Hi, my name is Stefan Farier from Nation's School of Sixth Form Studies, and I am a teacher of pure mathematics and physics. Today's lesson is a physics lesson, a very common topic that is taught at CSEC Physics, IGCSE Physics, CAPE, and even AS and A-level physics. So you can say that this topic is very fundamental to the study of physics at any level for exams or even above. So in this lesson, you're going to learn the following things. I'm going to teach you an approach for solving problems that are mathematical. We're going to talk about quantities related to linear motion and their definitions. Definitions are really important when you're solving problems. If you know what you're working with and you know what it means, knowing the units that are for a particular quantity is really easy to do. And we're going to discuss the 5 equations of linear motion, or as we like to call them, SUVAT equations. And then, with this body of knowledge, we're going to tackle some problems. A long time ago, somebody called George Polya wrote a book called How to Solve It. The method he describes has 4 steps that I will teach you to use in solving a variety of mathematical problems. As you can see, there are 4 steps. The first step is you gather the data. You identify the things that are given to you. You put a question mark next to the things that you don't know but need to solve for, or your x, so to speak. You're solving for the x. In creating your plan, you have to figure out how does the thing you don't know and you want to solve for relate to the information that you have. And you need to find out how you can exploit that relationship. The third thing is that you just do it. You have a plan, go and do it. And the fourth part is that sometimes it's possible to check your result to see if your answer is reasonable. Sometimes your answer might be too big. For example, a man doesn't weigh 1,000 kilograms. Or a ball cannot be moving as fast as the speed of light. So things like that help you to know which is the right way to go and prevent you from getting wrong answers. Now, distance is concerned with the length of space traveled. It's like running around the block. The distance you run is just the size of the block. Where displacement, on the other hand, if you run around the block and you end up back at your house, you've gone nowhere. You could have gone around the block 100 times, but you would have gone nowhere. So distance is the length of space you travel, but displacement really has to do with how much your position has changed from before. Whereas speed has to deal with how much distance you travel and the time you take. Where velocity now is concerned with the displacement that you experience and the time you took for that. Acceleration is a tricky thing because you have to know what you're dealing with. Are you dealing with speed? Are you dealing with velocity? In whichever case, it has to deal with the change in speed or velocity over time. Knowing these quantities, in addition to understanding what time is, will help you to better appreciate how we solve the problems you'll see in a few moments. The notation we use is SUVAT, this acronym. That's why we like to call them SUVAT equations, where, in summary, you have the notation we're going to use right here. S for distance or displacement, U for initial speed or velocity, V for final speed or velocity, A for acceleration, and T for the time taken. I'm sure you write this down. The first equation given here, V is equal to U plus AT. This is the simplest one. This comes from the definition of acceleration. So, in other words, if we want the final speed, we take what the starting speed was and we add whatever the change in speed occurred because of acceleration. Second equation is an expression of the distance traveled because of the average speed, which is half the starting and final speeds or velocities times the time taken. That gives you the distance traveled or displacement, whichever one you're working with. Third equation is another expression of distance or displacement in terms of the initial velocity and the time with the acceleration. And the pattern that you notice when you look at these things is that each equation has 4 quantities in them. And you'll see that in a bit when I show them all to you. The fourth equation is similar to the third, except that you use final velocity. And the fifth equation relates the final velocity, initial velocity, acceleration, and the distance or displacement. In summary, these are our 5. The 5 equations of linear motion under constant acceleration. Now, as I had a note before, you cannot use any of these equations if acceleration is not constant. So if you're accelerating and that acceleration is changing, these equations don't apply anymore. You have to use calculus for that. But once you have a constant acceleration, these equations are fine. So, as you can see in each of these things, look at them all. Each of them involves the use of 4 letters, 4 different letters. And the strategy that we use is this. When you write down your information, usually you'll get 3 pieces of information and 1 unknown. Or probably, if it's a more complicated problem, you might end up with something else. But usually, you get 3 pieces of information and they ask you to find 1 other quantity. Your task is simple. Look at these equations and figure out which one of these involves the 3 that you have and the 1 that you don't. And the one that you need to find, of course. So you will then write down your information, you select the appropriate equation, and then use it. Now you have some problems to solve. First problem we have is shown here. A particle is moving in a straight line with a constant acceleration of 6.0 meters per second square. As it passes point A, its speed is 20 meters per second. What is its speed 10 seconds after passing A? Now, I'll give you a moment. Think about it. Think about if you think you can answer the question, go ahead. Otherwise, I'll give you a minute to think about it. See if you can start to come up with a plan, and then we'll work together. Now, the first step is gather your data. Consider what you have. And here is the system that I'd like you to use. Write this. SUVAT. And now let's go through the question again. And let's populate under here what kind of information we have. So, particle moving in straight line, constant acceleration of 6.0 meters per second square. Okay. As it passes point A, its speed is 20 meters per second. So here, the initial speed, 20 meters per second. We want to know what is its speed after. So we don't know this. And do we have, what's the last thing that we have? Do we have any distance or displacement? Do we have time? If you said time, that's correct. So we have 10 seconds. And the task here, and the 5 equations will now come back up, you have to identify what equation do you know has these 4 things in it. Now, a good candidate seems to be this one. Does this have everything that we need? Let me see. B, we don't know, so check. U, check. A, check. T, check. Okay. So we have used all our information, and this is very important too when you're answering questions. Have you used all the information that's available to you? Unless, of course, somebody is trying to trick you by giving you information that is irrelevant. But in this case, all of the information is relevant, and we have our unknown, which is V. So let's go ahead. Always use your units. So if you just wrote 20, as some of you like to do, 20 what? $20, 20 mangoes, 20 chickens, 20 goats. We don't know. Until you say what the quantity is, nobody knows what you're talking about. You can't just say 20 plus something. You have to say the number and the unit that comes with it to express a quantity. That is proper presentation. Plus the acceleration, meters per second square. So 6.0 meters per second square, and our time is 10 seconds. Now, if you remember BODMAS, this calculation will be easy. So we will have 20 meters per second. Now, first let's work on the units that we'll have. Now, what's happening here, to understand how these units work together, which I'm not focusing on in this lesson, but you must have an appreciation for the laws of indices. In this case, we have per second squared times second. In other words, if I was to do a little sidebar up here, that would be s to the minus 2 times s, which would be equal to s to the minus 2 plus 1. What would that? Minus 2 plus 1. What is that? The answer, we have meters per second. Or you would have an index of minus 1. And the number we're ending up with here, 6 times 10, that's 60. And 20 plus 60, that's 80 meters per second. That's our first solution. Now, with an acceleration this large, over such a time interval, it only seems reasonable that the final velocity is more than the first. The acceleration wasn't negative, so it wasn't slowing down, it was speeding up. So the final velocity, more than the initial velocity, that's speed, sorry, that seems reasonable. If you got that right, good for you. But if you didn't get it right, that's okay. This is a learning process. When you make mistakes, you ask yourself, why did you make a certain mistake? You reflect on it, and then you get better. Don't beat yourself up about it. We're all learners. Next question. Question 2. Car starts to accelerate at a constant rate of 0.80 meters per second squared. It covers 400 meters whilst accelerating in the next 20 seconds. What is the speed of the car when it started to accelerate? this is time for you to think about it. You are armed with the 5 equations of linear motion under constant acceleration. You've been exposed to my process. Some of you should already be able to begin coming up with the answer. Now, the first thing that we do, write down SUVAT. Right. We have SUVAT here. Remember that acronym because we know what each of these letters stand for. Now, the next step is to read through our question and identify what information we have. Now we're given a constant acceleration, which means that we have a full go ahead to use the 5 equations of motion, linear motion under constant acceleration. That is 0.80 and in meters per second squared. And 400 meters, what's that? Is that a time or initial final speed? What? It's a distance. And the next 20 seconds, which is the time, the duration of this event. What is the speed of the car when it started to accelerate? What is that? U or V? U? Okay, thank you. Do we need to find V? No, we're not interested in that. What is the next step? You can all tell me, you can blurt it out now. Find an equation that involves these things. And then solve for U. Out of the 5 that you have, and one solution may not be the only one. Which one is a good candidate? Is it the first one? V is equal to U plus AT. Well, we have U, A, but we don't know U. We have A and T, but we don't have V and we don't know U. Not suitable. The next one, S is equal to half U plus V times T. Well, it's the same problem with U and V. So we can't have U and V both in the same thing, even though we have S, but we didn't use A. So equation 2 out. Equation 3, S. We have to solve for U. U is there. T is there. And A. Feels good, but before you jump ahead, let's consider the other, shall we? Equation number 4 had VT instead of UT. We don't even know what V is, so we can't use that one. And the 5th one, V again, we don't know that. We can't have V and U in the same place. So we have V squared and U squared, so no. The only equation to use in this circumstance, equation number 3. Right. S is equal to UT plus half AT squared. Now what do we do? Well, some of you might want to begin putting in values. That's fine, but I would recommend that you should always transpose for the unknown quantity, or make the unknown the subject, then put in your numbers. That makes things a little less confusing. Because some people, when they would put in the numbers and then they try to solve for you, the clutter starts to confuse their working and get it wrong. So avoid that, make your life simple. Our goal is to find this guy. So we have a little task here. Huh? We have to make this guy the subject. We have to make him stand out. So let's go. how are we going to do that? Well, first, I might just want to take this term and move it over. So I will get, let me go over here instead, S minus a half AT squared is equal to UT. Alright? Then, what do we do next? How do we get the U alone? Well, here, T is multiplying the U. If we want to get rid of it, we have to do the reverse of multiplying T to both sides. What is that? What is the reverse of multiplying T? Dividing by T. So S minus half AT squared all divided by T, and that's equal to U. Now we have set the stage to solve our problem. Good work, people. So, now that we have our expression, the next thing to do is to put in the information that we have. Here, on this side of the expression, every letter over here, we have a number for. We have a number for S, we have a number for A, we have a number for T. So we're good. We don't have a number for U, and guess what? We have to solve for U. So, which means the answer should just pop out. But you have to make sure you do your calculations correctly. So we're going over here. Let's see. So we have 400 meters minus a half into 0.80 meters per second square times 20 seconds all squared. What is 20 squared? 400, right. Oh, right. Where's my minus? That is equal to U, right. Cannot forget minus. So, what do we do now? We will have 400, I'm taking this in baby steps. So, we will have 400 divided by a half, or 400 times 0.5, however you'd like to think about it, which would end up being 200, and 200 times 8 would be 1600, and that would end up being 160. Yes, some of you are already telling me, why did you forget this? Sarah, what are you doing? Just trying to see if you're paying attention. So we're supposed to put our T below here, and we have our 20 seconds. Good. So let's go. That'll be 400 meters. And our answer would be that the object, which initially had 12 meters per second, that was its speed. Next question. A stone is thrown vertically upwards at 10 meters per second from a bridge, which is 15 meters above a river. What is the speed of the stone as it hits the river? Now, sometimes I will give this advice. You have a problem that you need to think about, a bit more, that kind of seems a bit complicated. Sketch it. Draw a little picture. And it doesn't have to be a complicated thing. You're here. This distance here is what? Is 15 meters. You have a ball here. It will be thrown upwards at 10 meters per second. And we want to know, what is the speed as it hits the river? Well, river. It doesn't look convincing. This is not an art class. It's sketching. So that's fine. The ball will go up. And what happens when something goes up? It goes up and then it slows down and then it stops in midair and then it continues to fall until it hits the ground or is stopped by something. But in this particular case, let's see what are we gonna do. How do we tackle any question here? Gather the data, create a plan, execute the plan, and see if your answer was reasonable or not. Well, let's go. SUVAT. Nothing can stop us now. Alright. And here. What is the displacement? What is the distances we travel? It will go all the way up, then it will come back down. That's a long distance, isn't it? They didn't give us that. We only have a bridge that is 15 meters above the river. Alright, so okay, let's get back to that. Initial velocity, 10 meters per second. That's alright. Final velocity, we don't know, we have to find that. We don't have a time. Didn't give us acceleration either. Are we not sure about this long distance this thing will travel? Well, now we have to consider what is the meaning of displacement. Remember, they told you it's thrown vertically up at 10 meters per second, which means that we not only have a magnitude of speed, but we know where it's going. That sounds like a vector, and velocity is a vector. So which means that we have to think in vectors now. So this is initial velocity, like I said before. It means that we should consider displacement and not distance travel, because the distance travel will be this. So what was the displacement? This bridge is 15 meters above this river. The displacement, usually, by convention, up is positive and down is negative. Also, for future reference, right is positive and left is negative on a graph. Usually we do that. So at the end of this situation, this ball would have to travel 15 meters down. What would that be? Minus 15 meters. Alright. Minus 15 meters. But then we have one more mystery. The next mystery is, what is the acceleration? We only have two pieces of information. We have one unknown. We have no idea how long this takes. And we don't know what is the acceleration. In order to make this work, we need four things. Three things that we know and one that we don't know. Right now we have two things that we know, one that we don't know. What is the next piece? Well, what is acting on the ball? What is causing it to go? What is causing it to slow down and then fall down? What is that? Gravity. What is the acceleration due to gravity? Some people say 10. What we will say 9.81 meters per second square. And not just that, it is not just 9.81, because you would think it would be positive acceleration, which means it's going to get faster, or it's going to go up. It's an acceleration up, but that's not the case. This is not a rocket. This is an acceleration down towards the center of the Earth. So it's minus 9.81 meters per second square. And the equation that we have to use must involve these quantities. And which equation is that? Which one of these five equations here do you see involving the S, U, V, and A? This one, equation number 5. V squared is equal to U squared plus 2AS. You can check it if you'd like. Is there any other equation that we could have used? Maybe not. We must find V. But there's a catch here as well. But we'll get to that. For now, we have a plan. Use this equation, so use the equation. U square, in this case, will be 10 meters per second all square plus 2 times minus 9.81 meters per second square. And there we go. We just have to find out what all that stuff is. So you use your calculator. And you have mine somewhere in the house. Didn't bring it, but that's fine. You have a phone. Phones are calculators. We already know that 10 squared, 10 times 10 is 100. So that would be 100 meters squared per second squared. That's fine. What's the next part? That's 2 times, that's 9.81 times minus 15. Or 2 times minus 9.81. Now, minus times a minus is a good, a plus. So we have 294.3. What is that? That's meters times meter is meter squared per second squared. Then, obviously, we have to add 100. We're going to end up with 394.3. 394.3 meters squared per second squared. But that's v squared. People never ask you to find v squared. They ask you to find v. So how do you know get v alone? What is the reverse of squaring? We have to perform the operation on both sides of the equation that is the reverse of squaring v. What is that? Taking the square root. So the reverse of squaring is taking the square root. So we have to square root both sides. So v is equal to square root of 3.943 meters square per second square. But there's another thing. This is wrong. Tell me what the mistake is. Yes. We forgot our manners. Whenever you consider the square root of something, you have to take plus or minus. Think about it this way. 2 times 2 is 4. Minus 2 times minus 2 is also 4. Which means that the square root of 4, well, really, if you have x squared is equal to 4, x can either be plus or minus 2. So anytime you take a square root, you have to put both of these signs in, or else I will tell you you're wrong. So in your calculator, you would then compute the square root of 394.3. And that gives you, let's just take up to the first decimal place, shall we? Therefore, v is equal to 19.9. 19.9, and the square root of meter square would be meter, and the square root of per second square. So the answer is plus or minus 19.9. But they can't be right. The speed, the velocity when it's hitting the water can't be plus or minus 19.9. It can't be going up or going down. I mean, if this was quantum mechanics and a particle in some field, then maybe. But this is not about that. And a ball would never go up and down at the same time. And if you've seen that happen, then should ask for help. Anyway, which one is it? Is it going up? Positive velocity is going up, and negative velocity is going down. At the end, what is it doing? Is it going up or is it going down? Down? Yes. Because the ball is going down. It has a negative velocity. And what did I say? By convention, up is positive, down is negative. So the answer to this question is minus 19.9 meters per second.